Welcome to a series of lectures called Class, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm head of the chair of Class and Glass Ceramics at RWTH Aachen University. The purpose of this video series is to give background information on selected aspects of the lectures. The videos are not based on the structure and the sequence of the lectures. And with that having said, let's dive into the next topic, which is about nucleation in glasses. I will give you a description of a thermodynamical approach to describe nucleation in glasses. Before we get to that point, let's first discuss some basic principles. There is no nucleation and consequently no crystallization without supercooling. Nucleation usually initiates a first-order phase transition from a liquid phase to a solid phase. Also, there can be some liquid-liquid immiscibility, which can be the first stage of the nucleation. And I will present you the classical nucleation theory after VOLMER and BECKER. The total enthalpy of the system is the free enthalpy of the nuclei minus the free enthalpy of the melt. And in this case, if the nuclei has the lower free enthalpy than the melt, this difference in free enthalpy becomes negative, meaning the nuclei is more favorable than the melt and the nucleation will take place. At that point, I have to make an important remark. Please be aware of the sign if there is a plus or a minus in the difference of the free enthalpy, because some textbooks define this relation as I do here, for instance Vogel in his textbook Glass Chemistry, in which it is the free enthalpy of the nuclei minus the free enthalpy of the melt. There are some other textbooks who defines this delta G as the free enthalpy of the melt minus the free enthalpy of the nuclei. And in that case, the nucleation takes place if delta G is positive. However, for me, it's more logical to define the reaction in that way, that it takes place if delta G is negative. And this is why we take in this presentation the definition of free enthalpy of the nuclei minus the free enthalpy of the melt. So, as mentioned, the nucleation will take place when delta G becomes negative. And also another remark in the following slides, we always assume spherical nuclei. Certainly this is also not always true, but if we do not assume spherical nuclei, it makes the whole situation much more complicated. So now let's look at the nucleation, and let's assume we have a temperature which is lower than the liquidus temperature of the system. First, let's have a look at what speaks against nucleation. And against the nucleation speaks that the nuclei during his growth must use energy to build up an interface against the surface tension of the melt. And this energy can be described as the free energy of the interface per unit area times the surface area of the nuclei. And the surface area of the nuclei, in our case, where we assume spherical nuclei, is 4πr square as the surface of the sphere. So this is the energy that the nuclei must expend for enlarging his surface against the surface tension of the melt. Now, what speaks in favor of nucleation is that the nuclei, if the temperature is lower than the liquidus temperature of the system, is energetically the more favorable phase compared to the melt, which means the nuclei has a lower free enthalpy than the melt. So the change in the free enthalpy of the system in relation to its molar volume, which is the free enthalpy per volume of the nuclei minus the free enthalpy per volume of the melt, is always negative. And this depends on the volume of the nuclei, which in case of a spherical nuclei is 4/3 PR to the power of 3, which is the volume of a sphere. Now, these two relations are competing with each other. And if we combine these two relations, here for the basically energy that the nuclei gains, because it's more ordered than the melt when it grows, against the energy that the nuclei must spend for growing against the surface tension of the melt. And if this sum becomes negative, then there is a stable nucleation. So if this delta GV plus delta GS here becomes negative, then nucleation takes place, because the free enthalpy of the nucleation here becomes negative. In this presentation also please note that I always write the full names of nucleation or nuclei to avoid confusion by taking any abbreviations. Also, please note that it's usually quite difficult to determine the delta GS here for the energy that must be spent against the surface tension. And this is why this part is usually approximated by taking the surface tension itself as delta GS, which then leads to the equation as written here by simply substituting the delta GS against the surface tension. Now, this is so far the classical nucleation theory from a very simple thermodynamical point from VOLMER and BECKER. What I want to present to you now is a slightly different approach with a different explanation. Let's first consider the free enthalpy of the nuclei, which, if we assume a spherical nuclei, refers to a curved face and is therefore less negative or energetically less favorable than the planar face, which has no curvature. If we now write this simple relation in an equation, we have the free enthalpy of the plane nuclei minus the free enthalpy of the plane melt. But there is this energetic, I would like to say, penalty for the nuclei because the face is not plane, it's curved. And this then comes back to the area of the curvature, which is, in case of a sphere, 4πr square times the surface tension. So this is the energetical penalty that the nuclei has to take because of this positive surface curvature. Now, the total free enthalpy of the nuclei and of the melt is depending on the volume of the respective faces. And because we assume the spherical face, it's basically the standard free enthalpy of the nuclei divided by its molar volume times the volume of the sphere with the respective radius. And the same is true for the melt, which is the standard free enthalpy of the melt divided by its molar volume times the volume of the sphere. Please note that this has nothing to do yet with if the nuclei is curved or not. This is simply the calculation of the volumes and therefore of the total free enthalpy of the nuclei and of the melt. The values for G0 nuclei or G0 melt can be taken from the known tabulated books. Now, having these first not shape-related volumes and free enthalpies of the nuclei and of the melt, you can combine these and then add the, as I said, penalty for the curved face of the nuclei. And this comes to this relation here. So the free enthalpy of nucleation is the volume of the nuclei and of the melt, which are certainly equal if we consider the same molar volume, which is an approximation, but here in our case it's acceptable. So we have the volume we have the standard free enthalpy of the nuclei divided by its molar volume minus the standard free enthalpy of the melt divided by its molar volume plus the, as I said, energetical penalty of the curved surface of the nuclei, 4πr square times surface tension. Now let's have a look at this equation. In this equation basically it applies that G is H minus Ts. So we can rewrite this as a function of the enthalpy and of the entropy, both for the nuclei and for the melt. And transferring that to that equation, this also means that the free enthalpy of the nucleation is the volumes times the enthalpy minus T times entropy of the nuclei minus the enthalpy of the melt minus T times entropy of the melt, divided by the molar volumes, which in our case as an approximation we consider as equal, plus the penalty for the curved area. Now this can be further rewritten as mentioned here. This is simple mathematical transformation, and with having this form, let's have a look at what the enthalpy of the nuclei minus the enthalpy of the melt is. Well, this certainly is the negative melting enthalpy. And the same, let's have a look what the entropy of the nuclei minus the entropy of the melt is. And this certainly is the negative melting entropy, which is also the negative melt enthalpy divided by the melting temperature. And rewriting that further, we come to this equation where the free enthalpy of the nucleation is the volume times the negative melting enthalpy divided by the molar volume minus the temperature times the negative melting entropy divided by the molar volume plus the penalty for the curved surface. Please note that these two relations certainly only are strictly valid if the temperature is exactly at the liquidus temperature. As soon as the temperature is smaller than the liquidus temperature, this is an approximation. Now let's take this equation and go one step further. This can be further rewritten into the relation between the entropy and the melting enthalpy with the melting temperature. And if we have this form, some mathematical transformation gives us finally the volume times the negative melting enthalpy divided by the molar volume times 1 minus the actual temperature divided by the melting temperature plus the energetical penalty for the curved surface. Please note here also that this description in red only exactly applies for T equals the liquidus temperature. The error of this approximation can be calculated via a Taylor series, which is maybe a video I will make at a later point. However, it's worth to look at these dependencies here and make yourself familiar with these mathematical transformations. So now the question certainly is, what was the purpose of this whole mathematical game that we did? Well, let's look at this equation. The melting enthalpy, the molar volume, and the radius of the nucleation are certainly always positive values. There is no chance that you get a negative melting enthalpy, there is no chance that you get a negative molar volume, and there is no chance that you get a negative radius. As long as the melting temperature is always higher than the temperature of the actual system, this part of the equation is always negative. And it comes to this part, again, of the curved surface of the nuclei, which finally needs to be smaller than this part to allow nucleation. Now, again, what's the purpose of this mathematical game? Well, I think the melting enthalpy and the melting temperature are much more illustrative values. They are much more obvious than, for instance, the free enthalpy of the melt. But arguably, this is certainly my opinion. Now let's have a look at the final picture of the free nucleation enthalpy. This is a black curve here, which is the sum of the free volume enthalpy plus the free surface enthalpy. And because the free surface enthalpy has here a factor of 4 to the power of 2, and the volume enthalpy has a factor of 4/3 to the power of 3, in the beginning, this one here is dominating. And the free enthalpy of nucleation increases. However, at a certain point, certainly the power of 3 is much more overwhelming than the power of 2. And this is why at a certain size of the rate of the nuclei, the free enthalpy of nucleation decreases, and when this size of nuclei is reached, which is the critical nucleation radius, the nucleation takes place and is basically not stoppable anymore. And certainly the maximum of this curve, on one hand, gives you the critical radius of the nuclei, and on the other hand also gives you the critical free nucleation enthalpy. And with that, we are at the end of this video, and I trust it was helpful for your further understanding of class science.